has three main parts. I will start with the projects that I did on diffusion MRI images, following by my PhD projects, and at the end I will talk about my project JPL. Actually, I'm not sure how many of you are familiar with diffusion MRI. So, okay, good. I will start with a short introduction on diffusion MRI. Then all of you, can follow me using this presentation. You know that our body consists of too many water molecules which are moving in many different directions. And in fact, by diffusion MRI imaging, we want to measure diffusivity of water molecules in different directions. In the presence of white matter in our brain, diffusivity of water molecule will be restricted in the direction of the track. And here in the image below, you can see some axial images of the brain. For example, one slice here, and different images show our measurements when we set the direction of gradient in the scanner in different. Okay, let's say we set gradient direction in this vertical direction, and then we prepare this MRI image from the brain. Then these these intensities in the image, for example, for this top figure here, what it does tell us is that what is the probability of moving water in the direction of this gradient at this voxel, and we measure this for another gradient direction, and so on. Okay, and of course we can measure these parameters for any direction in 3D. Imagine this sphere, and imagine these blue, orange, yellow, green vectors. So we set gradient direction on the scanner on these different directions, and then we prepare these images for one slice. So for one slice in my brain, I would end up with, for example, with this blue, orange, yellow, green, corresponding to these four different directions. Okay, so for G1 up to JK, we have these measurements S1 up to SK, and we have one extra measurement for this slice when we only turn on a static magnet. In the diffusion community, usually what they do is that they model diffusivity of water molecule at each voxel by an ellipsoid. You know that an ellipsoid can be represented by a 3x3 matrix, a symmetric 3x3 matrix. And in fact, what we measure on the scanner is this S1 up to SK. We have S naught, and we know the B value on the scanner. We know the gradient directions, which are shown with G1, G2. These are 3x1 vector, and the aim is to make an estimation of these 3x3 matrix for each voxel of the brain. And you know that we can make an estimation of these metrics for each voxel of the brain, given these measurements by performing, for example, least square. And now we can represent each voxel in our brain or other part of our body, by this ellipsoid. In diffusion, studies, there is a famous diffusion parameter which is called fractional anisotropy, FA. FA is a function of eigen values computed out of these 3x3 matrix. So for each voxel, we make an estimation of the tensor. For the tensor, we extract its eigenvalues, and then this figure here is just visualized computed as a voxel wise. And this is color FA representation, where the green, red, blue encode direction of the eigenvector corresponding to the maximum eigenvalue. And we can do lots of cool stuff using these tensors, for example, tractography. By tractography, we can find what is the connectivity between different parts of our brain. You know that on the scanner, what we collect is that we have some measurements in Fourier. in diffusion community, it is known as K space. So we have some measurement in K space, which is equivalent term to Fourier space. And then we apply inverse of Fourier transform to reconstruct the image. But there are lots of limitations when we acquire these images. We cannot acquire a dense sampling of Fourier coefficients. Maybe we are limited only to sample some points inside this red rectangle here. And you can see that, oh, we are losing resolution because of this kind of limitation. And these images can be affected with too many different types of artifacts. One of them is called a spike artifact. For example, if we only have one right measurement in our Fourier space and we reconstruct the image, we will end up with something like this, which is bad. Another artifact is motion, because subject on the scanner might move during the image acquisition, which is roughly something about 20 minutes. Especially it happens for fetal imaging. And there is one challenging artifact, which is called EPI distortion, or echoplanar imaging distortion. This is a geometric distortion. And actually, this is my brain. If you check at my eyeballs in the image in the left side, you can see that they are stretched. And in the right side, they are compressed. It's a geometric distortion. And in this slide, I try to give you some idea why this distortion is happening. Assume that rho xy is the ground truth image of my brain here, and the scanner measures these Fourier coefficients. Okay, on the scanner, because of the inhomogeneity in the magnetic field, which is represented by delta V here, it introduced some shift in the phase when you are computing these Fourier coefficients on the scanner. So, in fact, on the scanner, what we do is that we start to collect data points in Fourier space line by line. So, for example, we first collect this information on the first line, and then the scanner collects information on the second line. So, this direction is called phase encoding direction. And you can see that this distortion is happening in the direction of phase encoding direction. And if we change the direction of phase encoding, the sign of this inhomogeneity will be inverse in this equation, and then distortion will from top to bottom. And this distortion is completely nonlinear. And after I become familiar with this kind of distortion, I noticed that in many published papers in diffusion studies, they simply address this distortion applying some affine transformation. So what they do is that they have this forward, they call forward this image in one phase encoding direction, for example, bottom to top is called forward image, and its inverse is backward image. So what they do is that they apply some affine registration techniques to correct for this distortion, which is not correct because this information is completely nonlinear. But the aim is to, given these two images, we want to end up with one image which is shown in the middle, and we want to find this pi transformation such that applying pi over forward image, we end up with this image, and applying inverse on backward image, again we end up. And of course, correcting for this distortion and diffusion MRI studies is very critical. To the best of my knowledge, there are 3 softwares which are correcting for this kind of distortion. And one critical question for us was that which of these softwares is doing a better job, or for example, which protocol should we use in our imaging. Let me explain a little bit more. So assume that we have a software to correct, given this forward and backward image, we correct the distortion, and then we can get some idea about the qualification of this image by rigidly registering this image to another image, a structural image. The modality of this image is different than these diffusion MRI images. On these T2 weighted images, there is no geometric distortion, like EPI that was happening in diffusion MRI. So a good correction the one which end up to a good alignment between these two images at two different modalities. So one critical question that we wanted to highlight it for people in the community was that, okay, you can acquire 3D images using different protocols, for example, sagittal images, coronal images, start like, constructing this 3D image of the brain, by slices, in coronal direction or axial direction. And for each of these, we have two phase encoding options. For example, for sagittal, phase encoding could be from bottom to top, top to bottom, anterior, posterior, posterior to anterior. So we want to see which of these, is better. That means that after correcting for distortion, for which one have better corrected image. And we did some quality assessment for this kind of thing. For example, given the images, the green here is, shows the structural image, and the red channel here is the overlay registered image. I will not go through the detail here, but all I need to say by this slide is that quality assessment of this data is very important. For example, another cool project that I was working on was that people in Boston Children's Hospital, they came to us and they said that it seems that something wrong with this scanner. Can you somehow do some quality assessment of this data and tell us whether we are right or not? So what they did was that they provide us some images of that scanner taken at different times, in 2014, 16, 17. And then we perform bootstrapping on those images, and basically we simulate data using those tensor fitting modeling. Again, I will not go through the detail of that bootstrapping section because of the time limitation, but the main message here was that our results show us that coefficient of variation of FA in here, the y-axis is actually what we did was that we measured coefficient of variation of one of the famous diffusion parameter, and now all of you know what do I mean by FA. So we compute FA, and for those computed FAs, we compute coefficient of variation, and this is the histogram of the coefficient of variation, okay? And we see that for blue curve, mean of the coefficient of variation is increased. And that means that, hey, yes, these images are bad. Coefficient of variation of FA is high. And this is another quality assessment that we did on diffusion MRI images. One very another, I would say, challenging problem regarding diffusion MRI images is that it's not easy to have a direct acquisition of high resolution of these images. I guess some of you are familiar with this equation. You know that SNR is proportional to the size of the voxel and is proportional to root square of number of averages. Let me explain it a little bit more. Assume that we have images with resolution of 2 by 2 by 2. And then we acquire image of resolution 1 by 1 by 1 millimeter. So this equation tells me that SNR of the high resolution image is 8 times less than SNR of the low resolution, right? So, okay, now we said that we want to improve the SNR of my high resolution image to the same level of low resolution image, at least. What can I do? One possibility is that you can acquire this high resolution image 64 times, following this equation here, align them, average them, and then, in theory, we can prove that, the average image, after averaging 64 images, the SNR of this image would be in the same level of the SNR of the low resolution image. But is it trivial to do that? If we can take those images maybe in 1 second, maybe you said that, okay, it's okay, we can acquire images 64 times from the brain of the patient. But in reality, we have images of resolution 0.7 by 0.7 by 0.7 of ex vivo, which was acquired within 5 days. So see, it's very challenging to have a direct acquisition of high resolution image. What we suggest to prepare these high resolution images was that we reconstruct high resolution image using rotated KS spaces. What do I mean? So here, these images show the part of KS space that we are sampling for each snapshot. For example, for this one here, we do not sampling of frequency domain information on these two black parts, but we have sampling of them in here. So we have high resolution information in this direction, right? But we lose them in this vertical direction. So each of these snapshots collects some high frequency information in different parts of Fourier space. And now we have these images. And this is the forward model that we consider in our work. We said that each low resolution image is, can be captured with a function of high resolution image. And P here is the downsampling parameter, P is the point discrete function, M is motion, plus some noise. But again, I will not go through the details, but the idea is that we have these low resolution images, and we want to make good estimation of high resolution image by, and we did this using an iterative method. And so here, I just visualized color FA of different low resolution snapshots. And this is color FA of low resolution versus high resolution image. And these results make neurologists, for example, much happier. And I think that you agree that low resolution image is much better than this. And these are some tractography results that we show that, using this reconstructed high resolution image, we end up with much better estimation of the tracks in our brain. Okay, another challenging problem in diffusion MRI is intersite variability. Let me explain it to you. What do I mean? You know that to significantly increase sample size and statistical cover of our studies, we do need to combine information of multiple sites. But it's not easy. Why? Because of the presence of this intersite variable. Assume that we have some traveling subjects. All of them are gender matched, age matched, all of them are healthy. So if we, for example, acquire MRI images, diffusion MRI images of these subjects at different centers, for example, Siemens scanner in Boston, Siemens scanner in LA, or GE scanner in San Jose. We acquire images of these patients, and then we compute FA of these patients at different centers. Because everything is similar between these subjects, it's reasonable to end up with, with something like this. That means that there is no significant statistical differences between our diffusion parameters between these subjects at different centers, right? I am hoping that this makes sense to you. But this is what we see in reality. So, for example, FA measurement in one center, mean of them is 0.3, and in another center, mean of FA measurement is 0.2. That means that we see significant differences between these two sets of data. And this is not correct. All of them were the same. Even if, it was interesting to me that even when you have two Siemens scanner and you set all the parameters into a scanner exactly the same, after you do this kind of analysis, again the results show you, there are significant statistical differences. So what we did was that we said that we do need to harmonize these data. And of course, you can say that, one simple method is computing z-score of parameter, but this z-score is not a good idea because it is highly affected by, for example, number of population that you have in your data set, or you can say that you can do some other statistics, but covariate analysis, for example, but it's not clear to use which linear or nonlinear function we should use to correct for these differences. But in this pipeline, we were given some images of subjects which were age match, gender match, healthy. We make sure that all of these subjects are similar to each other. We have images at different centers, center green, for example, Siemens in Boston, and red, Siemens in LA, and so on. And in the output, we harmonize those images with respect to one of those centers. We set one of them as our reference site, and we harmonize them. So they're very basic ideas, in very simple language of this harmonization technique is that we extract some rotation invariant features from subjects in different sites. We compute expected value of them. We see what is the delta difference between those rotation invariant features, and then we try to correct for it. And now let me explain a little bit in more detail. So in target sites, we have these images of different subjects. Do you have any questions? No. Okay. So if you have any questions, feel free to ask me anytime. So in reference site, we have images of different subjects. We start by segmenting different regions of the brain using a well-known software, which is called free software. And then within each region of the brain, we have some voxels. For each voxel, we represent it using spherical harmonic coefficients. And these are the example complete coefficients for one voxel. You can see that the orders are 0. Why? Because this signal here is symmetric. And then we define rotation invariant features as L2 norm of the coefficients at different levels. It has been shown that L2 norm of the coefficients of spherical harmonics are invariant to rotation. So this is just visualization of the those rotation invariant features computed at each voxel. At each voxel, we have these three features at different levels, right? And then for each region of the brain, for different subjects, here y-axis represents, for example, RISH features at 0 level. So we compute expected value of RISH features for region, for example, corpus callosum of subject 1, of subject 2. We do the same thing for the images in reference site, and then we compute this delta difference between the expected value of these rotation invariant features. And we compute this delta for other levels, for second order, fourth order. And then the idea was that now that we know that there is this much difference between the energy of the signals at different levels between the images at different sites, we try to correct for it. We try to move them to the same level. So we define pi function like this, and then we start to backpropagate this information to the spherical coefficients at each voxel. So for each voxel of the brain, we add this delta to the rotation invariant features, and then applying some other mapping function, which was a scaling function. These are detail of the methodology, but my main message is that by this technique, we can we can correct for this delta difference between the energy of rotation invariant features of the subjects in reference and target site. We do this for all regions of the brain, and these are some results. Again, we start by some subjects which were age match, gender match, all of them were healthy, and because of that, we do not expect to see biological differences. Yeah. So our null hypothesis was that the mean of our rotation invariant and spherical harmonic coefficients should be similar for subjects in target and reference site. So what we did was that, so we have subjects in the reference site, which is shown in green. We have subjects in other target sites, which are shown in red, blue, purple. So what we did was that we compute those rotation invariant features, and we compute p-value of our features between reference site and target site, before harmonization and after these are just some, in this table, which we said that how many subjects we had in our centers. And back to this table here shows the computed p-value. And the take-home message of this table is that, look, before harmonization, all p-values shown in blue, they are less than 0.05, which says that there is significant difference between RISH features in reference and target site, which is not correct. But after harmonization, all those p-values are above 0.05, which is good. That means that we are doing a good job to harmonize our data. And another good thing about our methodology is that we keep, after harmonization, we keep within site coefficient of variation. What does that mean? Is that, okay, assume that, for example, me and you go under the scanner in Siemens in Boston, and because, for example, we are two female, age match, gender matched, hopefully healthy. So, but you know, my brain is different than yours. So we should see some differences between the measurements of my brain and yours. And after harmonization, after harmonizing these two brains, we still should see that much difference. And this is some TDSS results. Actually, what we did here is that we have different subjects. We register all of these subjects to a template, and for this template we have white matter, segmented white matter, and then for each one now we have correspondences between the voxels among all the subjects, and we compute those p-values voxel wise. And whatever is shown here on this red rectangle, these are the computed p-values before harmonization, and whenever something is yellow or red, that means that p-value is less than 0.25, which is bad, but after harmonization, all the p-values are green, which is good.
So, quick question. So, what's the source of these differences? Is it some intrinsic, parameter setting in the machines? Also, you said that even the same parameter can generate, or it's maybe some external, local, I don't know, magnetic field in the room or something like that.
Actually, excellent question. These are, for example, one possibility is the magnetic field inhomogeneity, and it's really not easy to make a scanner with homogeneous magnetic field. This is one possibility, and the coils that which are used in different scanners, this is another source that lead to this kind of intersite variability, and there are lots of MR physics based reasons that they try to explain why this is happening, and I think that it's still an open question. And now I will switch to my project during my PhD. My PhD project, one of the projects that I was working on, we want to design this pipeline for skin lesion tracking. The input to the pipeline was a pair of images taken from a same patient at 2 different times. For example, take one image now, and 3 months later, we take another image of the back of the patient. And in the output, we want to report location of disappearing mole or new appearing mole. Or for 2 corresponding mole, we want to say, is there any change in size, texture, color of mole with time or not? Why we were doing this? Because it has been shown that pigment skin lesions, PSL or moles on the back of the patient is an important risk factor for malignant melanoma. So that's why we do need to have this mathematic pipeline. In this table, I try to summarize the objective function. Actually, I forgot to say that we break down our pipeline to 3 different subproblems: skin region segmentation. We first start to segment the skin region of the back of the patient automatically, and then within that region we detect moles, and then given the moles in image 1 and image 2, we perform matching between them. And on this table here, I just try to summarize the objective function of these 3 different tasks. Landmark detection, yes or no mole. I use term mole sometimes instead of PSL. PSL detection and PSL matching. And basically, these objective functions contain three different terms: unary, binary, ternary term. So the first task was skin region segmentation, and in our pipeline, we define a skin region as the region within a polygon introduced by a set of anatomical landmarks on our body. We define 8 anatomical landmarks: neck, shoulder, armpit, hip points in the left and right side of the body. So in the first task, we do need to detect these anatomical landmarks automatically. Our objective function to perform this landmark detection has unary and binary term, and for unary term, what we did was that we did feature engineering and extracted lots of different features, like local binary patterns, R features, wavelet-based features, and then train a random forest classifier 8 times because we have 8 landmarks. So at the end of the day, at this stage, for each voxel, we would end up with some probabilities, and that probabilities would say, what is the probability of this pixel belong to, for example, neck right? Those probabilities for neck right are encoded to red channel, and we do this for all other landmarks. In this figure, those computed probabilities are visualized, are encoded to red, green, blue channels, but you can see that these probabilities are not good enough to make a good prediction of the position of landmarks, right? But we know that these landmarks respect to a specific structure. We know that, for example, neck right is always on the right side of our body above other landmarks. That's why it makes sense to add this regularization term to our objective function, which encode these kind of structures to our objective function. And we optimize it using a dynamic programming approach. Actually, I just want to say that this algorithm is a good job on our skin back images. I just applied it on some volumetric images, and we were one of the winners in the challenge 2014. Also, people, some people had X-ray images of lizard, and they said, can you detect landmarks on these images for us? And then I applied it on these images, and we did a good job. Okay, now that we have this polygon of the skin region, we make an estimation of the position of moles by a simple regression tree algorithm. And now the last step is lesion matching. Now we have these detected moles on the back of the patient in image 1, on the back of the image in image 2, and this is the graph matching problem. And we solve this problem by binary labeling of the association graph corresponding to these two graphs. So assume that we have graph 1 in purple, graph 2 in orange. In the association, each node in the association graph, for example, this node, represents one inter-edge connecting one node here to this node here. If we label this node with 1, that means that this is an active edge. These 2 points are corresponding to each other. And in this objective function, in fact, we try to predict what is the label of the nodes in the association graph. And in that binary ternary term, we measure agreement of the matching between the 2 nodes of the graph, or 2 edge of the 2 graph, or 2 peaks of this graph. And I noticed that our matching algorithm were found to end up with wrong solutions that is in this, after applying this matching algorithm, when 2 moles are close to each other, the solution might not respect the topology of the graph. But what do I mean was that here corresponding edges are shown with the same color. For example, purple, this purple here is matched to this purple here, and orange is matched to orange. So order of points here is clockwise, order of points here is counterclockwise. So, okay, what should we do? What we did was that we designed some Jacobian-based descriptors and used those descriptors, fit them to our matching algorithm, and it encouraged our objective function to end up with solutions which respect the topology of the matching. And these are some values. So we evaluate this method over 97 pair of images provided by British Columbia Cancer Agency. Another thing that I did was that I worked on dermoscopic images. Dermoscopic images, again, these are skin images. So the idea is that after detecting those suspicious moles on the back of the patient, we do need to take high-resolution image of those images. They are called dermoscopic. And in our data set for each image, we know, at our ground truth, we know that whether some abnormalities appear or not appear on that image. For example, as I know you cannot see this, but this is the ground truth that we had for each image. Our abnormalities was pigment network, dots, streaks, or vascular structure, and it said whether yes or no, whether these exist in the image or not. So we do need to perform this classification task. And again, I did some feature engineering, for this task. And in our data set, we had at that time about 674 images. The feature that I was extracted was we call it context of eigenvector. We had some beta-wide features, of course. You know all of these beta-wide features. I am sure that all of you are familiar with these beta-wide features. And then what we did was that we applied, for example, random forest SVM to perform this classification task for us, plus some semi-supervised techniques. We consider each image as backup instances. And for example, when we know that, for example, this image is positive, we try to make an estimation of the label of those instances. Those semi-supervised techniques were contained latent SVM and MySVM. And the take-home message of this slide was that we have classification results of these different classifiers, and the results said to me that when we make the final decision using the predictions using all of these classifiers, classification results improve. So that means that interval learning is good when you don't have limits in terms of, for example, running time or memory. So apply as many classifiers as you can, and then make another learning over them to make the final decision. Okay, and this is the project that I did on JPL. The idea was that we were given about 10,000 images of Mars. Orbiters take some images of Mars, and then they send those images to the Earth for scientists. But it's costly that, when they are passing these images to the Earth, if they were, whatever they took, and then they send it to the Earth, that image might not contain useful information. So that's why they want to pick good images and send them to the Earth. Okay? For our data set, for each image, we have a label. And the total number of labels were 8, which said that whether this image contains, for example, a spider, a streak, dark dune, bright dune, or nothing. Okay? Or crater. So it was a multi-class classification task. And in fact, these 10,000 images were extracted from 180 full high-rise images. So they have 180 of these high-rise images, and then for each image, they extract 500 patches. And then at the end of the day, in our final data set, we have about 10,000 images. And this was the pipeline that I designed. We have a config file. In the config file, we set, pass to these images, to the ground truth, and then the user can turn off and on many different classifiers, including SVM random forest, extremely random forest, logistic regression. For example, we perform some hyperparameter on these classifiers. The pipeline also contains CNN. I use AlexNet to perform this classification task, and we train, do this, for example, 5-fold cross-validation on our data set. In the output, we automatically report the PDF, which shows the efficiency of these classifiers. And this is just one example of what is reported dummy classifier because their data set at JPL was highly unbalanced. They had about 8,000 samples of one class, and for other classes, they had about 200. So I want to see, okay, what is the, so what if we only have dummy classifier? And they had one library to extract some global features. That's why I said old features. Actually, these green and blue show classification results using the winner of the feature-based classifier, which was random forest hyperparameter tuning. And I did some feature engineering, and the results were that yes, we did a good job to improve the classification results after using the new features. And all of these are results provided by CNN. So the green one is the classification results after fine-tuning. And what are these? So what I did was that I extracted just SC6, SC7, SC8 of AlexNet and fit them to our feature-based classifiers. I want to see what was what they are doing after using these features. And you know that the size of these features is something about 4,096, which is huge. And people in JPL, they are for projects like these, they are very restricted in terms of memory issues. They have, and then you do not have that much flexibility to use, for example, CNN, many different layers, or too many features. But what these results tell me was that okay, those features extracted by learned and extracted by CNN are excellent, but then one of the main challenging questions is that can we somehow extract similar features using, in simple way from our images and fit them to our feature-based classifiers and maybe improve the classification results of our feature-based classifiers. And again, why? Because they are very limited in terms of memory, so they cannot use too many features, they cannot use too many things. And sure.
So in this classification task, how many classes are there?
8.
8 classes.
Just to get an idea, what is the size in memory of the feature classifier versus like a convolutional neural?
I think that so it depends on, for example, let's compare it in terms of parameters that you are learning. So how many weights you have to say,
I'm just wondering, like the megabytes.
Megabytes. Actually, I do not have a. I had it with some of my reports on which we compare this classification in terms of memory size versus running time, and even running time of test was much higher compared to feature-based classifiers. And I don't remember the exact number, but even in logarithmic scale, there is a huge difference, and it passed all the constraints by JPL.
Sorry, can you also, so this classifier FC the number, so these are CNNs?
Actually, the yellow up to this gray one, in fact, these are outputs of feature-based classifiers, random forest classifier, but the features which were fit to this classifier, they were CNN-based features. For example, the yellow was for yellow, our features were features at fully connected SC6. So we use them. These are CNN-based features fit to feature-based classifiers.
It is the same CNN that's shown at the
yes.
At the end.
Yes.
So if you basically take that CNN and you supply that features that you learned to random forest, so this is what you get.
Correct. And actually, maybe you can say that, oh, I see this SC6 and SC6 tune. What does that mean? Okay, that means that we just use a learn AlexNet. We did not do any fine tuning, and fit the features, fit the image, extract those features. And another time, I did fine tune the AlexNet, and I use after I did fine tuning, I used those features to fit our supervised classifiers. And I thought that my hypothesis was that, okay, after I do fine tuning, the results should goes up because now this network is fine tuned for my input images. But the output results did not confirm that. And then I tried to make a justification for that. Well, for example, one justification was that I did not do hyperparameter tuning. Another thing was that, oh, our data set, the size of the images that we have was 10,000, which was not comparable to the images used to, to train the original network. And I don't know if I did answer your question or not. Any other question? And thank you so much. That was my.
Can we go back to?
Okay,
No, go ahead.
So yeah, I mean, I'm just wondering. So you have shown some results on a very specific sets of images, from brain to satellites, and so most of the work that is done on a ISI on vision, I assume they basically are concerned with more general types of images. So what do you think, in terms of basically how much effort would be needed to generalize some of the things that we have talked about to apply to problems that are more ISI centric?
Actually, this is an excellent question. And before this chapter, I was with Dr. Hill, and I think that she asked me a similar question. And actually, in my meeting, I mentioned to her that after working with images with different modalities, especially after moving from medical images to space images, I found that, people in different groups, the first impression is that they are working on completely separate tasks, but the reality is that they are doing similar things. And even for medical images, maybe some people are working, for example, geometric distortion for brain images. This is just one example, and some other people are working on heart images. But what I feel was that sometimes they do not aware of the softwares which are used on this group, and it's perfectly beneficial to use those softwares for other groups. I think that my understanding from your question is that how much effort do we need to, for example, if we have two different modalities, let's say agriculture data set and some medical based images, and for example, we notice that, these people need to perform, for example, classification or segmentation. Same thing is happening here, and can we use those things for other groups? And I did not do this so far, but my answer is yes, definitely we can, but maybe it's a matter of maybe doing something like hyperparameter tuning, or maybe, for example, if we have a loss function in our objective function, trying to modify it a little bit. But I think that it would be very, very nice if one day, for example, people from one level upper who are seeing other people working on different modalities, different type of images, find those similar tasks and say that, okay, you people can make benefit from each other and pass those software within each other. But I don't know if I answered.
Thank you.
Yeah, I actually have a question. When you're doing the brain, what is the word, harmonization? I think there's something that in the deep neural network community that this is very similar to the cyclocan case, correct? You have two domain of the data. Have you ever think of applying, this kind of deep learning technology to the problem that you work on?
Actually, I said you were thinking about Psychiatry, right?
Yeah.
To be honest, specifically for diffusion MRI, I'm not sure how easy to formulate harmonization using specific Psychiatry. I know that people in learning, actually, I had some meeting with them regarding this harmonization technique. I know that they are using CNN to do this harmonization technique, but not using Psychiatry. I'm not sure. I need to think about it. But with Psychiatry, I think that you have an amazing. It might be an excellent way to correct for EPI distortion correction because but basically we have this forward image, backward image, and then finding this middle image, and we know that this mapping is inverse of each other. So that tells me that Psychiatry is a good way to correct for this, but there are lots of challenges. I try to think about it to correct for the EPI distortion, but to be honest, I did not think about Psychiatry for the harmonization, which.
Is there any specific reason why you're still using AlexNet for the object classification on the Mars?
No. We just there was no any reason why. Because of this reason, I use AlexNet maybe. And actually, Inception much better because it has less parameter to learn compared to AlexNet. But we just try one of the simple frequency techniques. But even that simple method, we're doing much better job compared to feature-based classifiers. And yeah, that's it. But back to your question for harmonization using Psychiatry, I think that if we really can have a clear, formulation of solving this problem using Psychiatry, it's a very interesting idea. And maybe highly cited in future near.
Can you go back to your bar chart for this one? I'm just curious because the gray versus the green lines, the last two bars, this is basically FC8 features minus the last layer and then fit into a classical classifier. Can you explain the jump between these two? Because if you're using the same...
Actually, it's an excellent question. What you are saying is that, in fact, we have these features, and at the end, we have maybe just one simple classifier. And now you are using those features with them to randomize classifier, and here there's one last classification.
Could it be that, because here I noticed you don't have FC8 tune.
Correct. Because, you know what is happening? Because in this layer, we have 100 features. This is the output of the final AlexNet. And in that, when we do fine tune for that, we just replace that 100 features with 8 output for our classifier. You see what I mean? Maybe what I should do was that maybe I should add one extra layer to the current network instead of just changing number of outputs of this layer. You see what I mean?
Yeah.
It was clear.
Yeah.
But it was excellent.
Any other questions?
Yeah. Irrespective of exact algorithm, can you talk about some intuition on the difference of 3D image data set versus a 2D image data set?
Your question is that
MRIs have voxels, but crater classification is 2D pixels.
Let me explain my understanding from your question. You said that, for example, assume that you have a classification task, and we have images, 2D images and 3D images. So what are the differences? So what are the challenges that we have to address this task? Are you asking?
Just like the difference of the mathematical considerations.
So my first answer is that again, maybe I should go back to this perspective. No matter what it said. Actually, I have two answers. Maybe they are in two opposite perspectives, but this is my opinion. I did work on imaging and modalities. dimensionality, 2D, 3D, 1D, 4D, ND, but and make different tasks, classification, segmentation, registration. But I think that at the end of the day, we are solving very similar objective function to address those things. You see what I mean? For example, even for so the final objective function is similar, maybe, but of course, when you are increasing dimensionality in your, this is the others. The first thing is that they are similar. You know, yes, the dimensionality is increased, but what they are doing, no matter what is the dimensionality of the data, no matter what is the task that you are working on, registration, segmentation, I think that it's something like different cities, and one of them can be inverted to another one or transformed to another one. Maybe there is a registration techniques, and I believe that you can use those registration techniques to perform segmentation. But all you need to do is to find this kind of nice transformation function between these two problems. So they are similar. But the my second answer is that for sure, when you increase the dimensionality of your data, maybe you think that, oh, you have more data, so which is good. But working with higher and higher dimensionality is much more challenging, much more challenging. Is my thing. I don't know if did I answer your questions?
Yeah, I was just wondering a little bit about the challenges, but
so, for example, you know, during my PhD, I worked on images, and then during my postdoc, I worked on this diffusion MRI and the dimension. And when I worked on these images, dimension was increased, but I found that, oh my God, these are much more challenging than issues because of the presence of those too many different artifacts on those images. You know.
Maybe one specific question in that regard. So let's say if you are applying CNN, in 2D is just the patches, like so there like accepted way of deciding what the neighborhood should be for convolutions in the tree.
Actually, what people do in 3D, you know, many people, there are lots of, let's say we have too many techniques implemented for 2D. And we want to see, can we use these methods to perform our segmentation task in 3D? And then, you know, one possibility was that, okay, for example, if you want to do a skull segmentation of brain images using those 2D things, you can formulate your problem. You can say that, okay, we can have a slice of sagittal, coronal, axial, and we can make a 2D image by concatenating of them. Now, this is the thing that, back to the thing that I said, you can define this kind of transformation between different tasks or different modalities. So what we can do is that we can convert our 3D problem, our 3D segmentation task to 2D segmentation task. How? Okay, you have these slices in 2D, maybe axial, sagittal, coronal, and then use that. And maybe again, maybe use that for that. And then for sure, when you are formulating this, you can make sure to keep information, spatial information of nearby voxels. And there are ways, I believe, that to encode this kind of information.
Thank you.
Okay, stand the speaker one more time.
No, it's just of course
I know, I do that.
So,
Sleeping leg.
How would you let me drop that? My office, you're going to go.
I'll go to drop this too, and we can meet in the lobby downstairs. 5 minutes?
Sure. Sounds good.
Thank you.
Ready?
Yes,
This is yours or?
Actually, no, I could not connect mine.
This is not yours.
No.
Okay, so we'll just leave it. No, don't worry about it.